everyone. My contribution was given live at the conference, but due to some technical issues, I'm now presenting it again in an asynchronous format. My name is Lorenzo Antonioli. I'm a research fellow working with the Metallurgy Group of the University of Ferrara, and in November 2025, I will start my PhD project focused on the optimization of secondary aluminum alloys for a green transition in foundry industry. Today, I'm going to show you the experimental results of a preliminary comparison between two specific quenched and tempered steels. The activity was carried out in cooperation with Berco Company within the CIE 2023 research project of the University of Ferrara. At present day, the company is focused on the industrial production of steel components for heavy-duty applications, such as undercarriage track links and other solutions for the truck machinery industry. Therefore, this research project concerns a complete characterization of selected quenched and tempered steels used for the industrial production of such mechanical parts. It is well known that quenched and tempered steels are used to produce components which require suitable mechanical properties, such as strength, hardness, toughness, and also fatigue resistance. In order to ensure these properties, these materials undergo specific heat treatments which consist in quenching and tempering following austenitizing. Particularly, tempering includes different temperature ranges called stages, and each stage is associated to a specific resulting microstructure within the material. In this case, it is also important to state that, according to some literature studies, increasing tempering temperature seems to decrease the fatigue resistance of quenched and tempered steels. Nowadays, steel industry has to face important challenges regarding the optimization of heat treatments in order to get valuable achievements towards a more sustainable production. The CIE 2023 research project of the University of Ferrara has these types of targets, and so the very first phase of the project requires a complete investigation in terms of microstructure and mechanical properties of selected quenched and tempered steels according to the current heat treatment parameters employed within the industrial production. The next phase will see the optimization of these heat treatment parameters, and the final goal is to reduce the environmental impact due to the industrial production while maintaining or improving the current mechanical properties highlighted within the very first phase of the project. So, the preliminary experimental results we obtained so far concern two specific quenched and tempered steels, and today I will refer to them as Steel A and Steel B. The first one undergoes a low environmental impact heat treatment since it is tempered at low temperature, while the second steel, which is actually a carbon neutral steel, is tempered at higher temperature. In this case, as I said previously, both steels are used to produce mechanical components such as undercarriage track links. And the company we worked with directly gave us the tensile and fatigue specimens we used to perform tensile and fatigue testing. Subsequently, the very first phase of the experimental procedure consisted in tensile testing performed on tensile specimens. In addition, metallographic samples drawn from broken tensile specimens were used to perform microstructure analysis and also Vickers hardness testing. So, as concerns the resulting microstructure of the investigated quenched and tempered steels, the first one, so Steel A, exhibits a fine-tempered martensite, while Steel B exhibits a sorbated microstructure because of tempering performed at higher temperature. Precisely for these reasons, Steel A exhibits higher tensile resistance if we take into account both the ultimate tensile strength and also the yield strength. In fact, tempering performed at higher temperature in case of steel B consisted in a softening mechanism of the material and thus a decrease in tensile strength. In terms of ductility, steel B shows a slight increase in ductility because of tempering performed at much higher temperature, but the most important thing we can assess within the present slide is that the ductility values are comparable if we take into account both the elongation after fracture and also the reduction of area after fracture. Now, moving on hardness test data, even hardness turned out to be greater for steel A with respect to steel B because of its sorbitic microstructure related to tempering performed at higher temperature. Hardness was measured by means of hardness profiles carried out on transverse and also longitudinal sections of metallographic samples extracted from broken tensile specimens. And we can see here in the present slide that although steel A exhibits higher hardness with respect to steel B, hardness values are almost the same if we take into account longitudinal and transverse sections of this metallographic sample. So we can assess there's no material fibering and so no wrong fibering processes affected the investigated components from which tensile specimens were extracted. On the other side, fatigue specimens underwent rotating bending fatigue tests according to the parameter included in the present slide. So the stress ratio was set to -1, while the granite cycles was set to 5 million cycles. The fatigue test data were analyzed by means of a biconditional probability stress life model, which was actually taken from the literature and which is also similar to other ones which are present in literature. This specific model, going briefly into the detail, considers both the finite life region of the SN curve and also the infinite life region by means of two conditional cumulative distribution functions, which are the orange one and also the green one. In this case, the first distribution function, so the orange one, is related to the log cycles to failure at a given log stress amplitude, while the second distribution function is related to the logarithm of the fatigue limit. Finally, we can say that the probability of failure of a fatigue specimen is the product of the two distinct distributions. In order to make it work, the model has 5 unknown parameters, which are estimated by maximizing the log likelihood function included in the present slide. And the first parameter, B, is related to the slope of the SN curve in the finite life region. The parameter A is related to the Baskin's law for the finite life region. And finally, the last 3 parameters are respectively the scatter parameter for the logarithm of the cycles to failure at a given stress amplitude, the logarithm of the fatigue limit, and finally the scatter parameter for the fatigue limit itself. The model also takes into account both the broken fatigue specimens and also the specimen that ran out. So here we can see the results regarding the fatigue resistance of the investigated quenched and tempered steels, and the SN curves are present together with the scatter bands related to the 1 and 99% probability of failure. It is evident that steel A exhibits higher fatigue strength and also a higher fatigue limit with respect to steel B, but this one has the lowest scatter of fatigue data. And for reasons of intellectual property, data were matched and reported as a percentage of ultimate tensile strength in terms of stress amplitude. These findings are actually in agreement with the literature studies, which highlighted that increasing tempering temperatures seems to decrease the fatigue resistance of the material because of a softening mechanism occurring within the material itself. Finally, the experimental procedure we adopted also included fractographic analysis carried out on one broken fatigue specimen for each steel, in order to highlight possible differences in terms of fracture behavior by considering two distinct tempering temperatures. And in this case, we can see that both specimens exhibited crack initiation sites located at the external surface. So we are dealing with the typical morphologies related to rotating bending fatigue tests. And together with these crack initiation sites, the specimens exhibited a flat crack propagation region and finally a final failure region, which appeared more fibrous. In this case, at high amplification, we detected that crack initiation sites were associated to surface and subsurface defects, which eventually promoted the initiation of failure. Apart also from fatigue striations detected within the crack propagation region, we also highlighted the presence of dimpled features within the final failure region. And the presence of such morphologies could be justified by the evidence of specific non-metallic inclusions, such as manganese sulfides and also titanium nitrates, which were actually in agreement with the chemical composition of the investigated steels. In fact, such non-metallic inclusions were detected not only for steel B, but also for steel A, as we can see in the EDS spectra included in the present slide. So we can assess that although we are dealing with different tempering temperatures and so different heat treatments, both the investigated quenched and tempered steels exhibited the same morphologies in terms of rotating bending fatigue behavior. So, just to sum up, a microstructural and mechanical characterization of two specific quenched and tempered steels was carried out, and the preliminary results were presented today. Steel A exhibits higher tensile resistance, hardness, and fatigue strength because of the fine tempering multi-city microstructure due to tempering performed at low temperature. Conversely, steel B shows better ductility thanks to the sorbitting microstructure together with a low scatter of fatigue data. In conclusion, we can assess that within the stress amplitude range where steel A could be deployed, this material has eventually a better combination of mechanical properties. In terms of future outlooks, these preliminary results I discussed about today are useful to investigate the mechanical properties related to the current heat treatment routes employed within the industrial production. Then, the automatic tests will be carried out in order to elucidate the critical temperatures and the transformation durations of both quenched and tempered steels. And all these findings will be used to design and perform new heat treatment routes, such as rapid tempering or also post-tempering. And the final goal, as I said previously, is to preserve or improve the current mechanical properties of the investigated quenched and tempered steels, while further reducing the environmental emissions within the industrial production. And particular attention will be given to the carbon neutral steel, which actually guarantees valuable achievements in terms of a green industrial production within steel industry. I would like to acknowledge Berco Company and the financial support of the CIA 2023 research project of the University of Ferrara, which made it possible to perform both bibliography, research, and also experimental activities. Thank you for your attention, and I hope you enjoyed this presentation.